Human rights matter, but conversations about rights can be polarizing, confusing, and frustrating. Lawyers Claudia Flores and Tom Ginsberg have traveled the world getting into the weeds of global human rights debates. On Untitled, a new podcast from the University of Chicago Podcast Network, they use that expertise to explore the stories and thorny questions around why rights matter and what's the matter with rights. Subscribe to Untitled, part of the award-winning University of Chicago Podcast Network.
Shalma, let me paint a picture for you. It's 1919, the first few months of that year. Albert Einstein is kind of the biggest figure in physics. Just a few years ago, he finalized his greatest theory, that of general relativity. And it made at least a prediction or two that was known to be true. It predicted Mercury's orbit better than Newtonian physics did. But despite this, I would say that at this point in history, general relativity was still a basically untested theory. If you just took a neutral look at the data, you wouldn't know whether this theory was true or not. The data didn't exist yet. But to Einstein, there wasn't really any doubt that this was a true theory. He was very, very confident that when the data finally came together, it would vindicate general relativity. It had to be true. To him, he said, and I'll quote, "General relativity was too beautiful a theory to be wrong." So if I look over the history of 20th century physics, you can find lots of examples of famous or prominent physicists expressing kind of similar sentiments. So Paul Dirac, for example, one of the main figures in the development of quantum mechanics, said at one point that, quote, "A correct physical law must possess mathematical beauty. And mathematical beauty is a quality which cannot be defined any more than beauty in art can be defined, but which people who study mathematics have no difficulty in appreciating." A generation later, the great physicist Richard Feynman said, quote, "You can recognize truth by beauty and simplicity. Inexperienced students make guesses that are very complicated, and it sort of looks like it's all right. But I know that's not true because the truth always turns out to be simpler than you thought."
So does it really work this way? Can we really judge the plausibility of a theory of science based on a judgment about how beautiful it is?
So I think in the course of this podcast, let's talk about this, perceived connection between truth and beauty in physics. What these people really mean who advocate for this position. Is it really true? Is it really useful? And if it is true and useful, then why is it true and useful?
And before we get started, just a reminder that if you like our show and you want to support us, our Patreon is now online, where you'll get access to exclusive Ask Me Anything episodes where you can submit questions, and you'll get a free Why This Universe sticker, and most importantly, our very deep appreciation. So you can find our Patreon online at patreon.com/whythisuniverse. Or you can find it linked on our Twitter at whythisuniverse as well. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So it turns out that there are pretty much two camps when it comes to the question of beauty in physics.
There's one group of people, I'll call them the romantics, and they tend to be really drawn to these kind of sentiments. And I was one of these people when I was a physics student. I read all this history of physics where these people like Einstein and Dirac and Feynman express these views about almost being magically guided towards the truth through this aesthetic criterion of beauty and simplicity and elegance. And I love this stuff. I thought it was amazing, and
It makes for good stories, for sure.
Definitely makes for a good story. And then there's another group of people, and I'm going to call them the rationalists or hard rationalists. And they look at this and they just call bullshit. They just don't see any reason that a theory being perceived as beautiful should have anything whatsoever to do with that something being true, that theory being true.
So before we take sides in this debate, it's important that we address the question at the center of this all. What is it that makes the theory of physics beautiful? It's a very difficult question to answer just because of how subjective the experience of beauty is. Like, it would even be hard to answer why a certain painting is beautiful to some people, let alone something that can get as abstract as physics can. But if we look at some examples, we find that there are some common features among theories that physicists typically describe as beautiful. For example, in our last episode, we talked all about supersymmetry. Supersymmetry is a theory that can help us answer many of the deepest open questions in physics, from how to combine relativity and quantum mechanics to possibly answering what the dark matter is. And apart from all that, it's often cited as being a very beautiful solution to all of these problems. So why is that? Well, at the core of supersymmetry is pretty much one simple underlying idea, that for every fermion in the universe, there is a corresponding boson, and vice versa. With that one simple idea, you get all of these amazing consequences. The simplicity of the theory, in hand with its power, contributes to that experience of beauty and elegance that it invokes in some people.
Yeah, physicists are really drawn to theories that explain a lot of things with a small number of simple underpinning principles.
But of course, we don't know that supersymmetry is true. Let's think of an older, more well-established example. So before the early astronomers like Kepler and Newton, there was no well-understood connection between how objects behave on Earth and how things behave out in space. To many people back then, the heavens and the Earth existed in different planes for all they knew, and there was no reason to expect that how a rock behaves as you throw it is at all connected to how the moon moves around the Earth, for example. That is, of course, until we had Newton's theory of gravitation.
So the gravity that pulls an apple down is the same thing as the gravity that keeps the Earth in its orbit around the sun. You just need one principle, not two, to explain those things. Those are the sorts of things that physicists point to and go, oh, that's elegant, that's simple, that's beautiful. That's a big part of what I think most physicists mean when they talk about beauty of a theory.
So what does a complicated theory look like? One that isn't all simple and elegant.
Like, people talk about the standard model of particle physics being an ugly theory. And it just kind of seems like a whole bunch of different random stuff glued together. So the gauge group of the gauge symmetry of the standard model has three parts, not one, but three. It's SU3, U1, and SU2. Like, why all of that? And then there are, I think, 19 free parameters in the standard model. This is a bunch of ad hoc stuff just set to fit the data. It's not very elegant. It's not very simple. It seems kind of Baroque, maybe even contrived.
This preference for theories which are simple and elegant is also expressed in the famous Occam's razor. The idea is that if you have two theories that make the same predictions, you should choose the one that needs the fewest assumptions.
So let's consider a hypothetical. So say this morning I wake up and I can't find my car keys. I can offer various hypotheses. I could say, well, maybe I misplaced them. Maybe they're in my other pants pocket, or maybe I left them somewhere else. Maybe they're in my car's ignition right now, whatever.
Right. Or maybe a group of bees flew into your bag, took them, and brought them to their nest.
There you go.
Yeah.
two hypotheses, both of which agree with all the data we have. I would argue one of those is a lot more likely to be true than the other, even though they're exactly empirically on the same, footing.
Although if you, while you were looking for your keys, noticed a lot of bee stings, maybe that would change things. So we've talked about elegance and simplicity, but are there any other things that make a theory feel beautiful?
So one thing that some physicists are drawn to and they consider to be a feature of some beautiful theories has to do with the quality of uniqueness. if you have a theory and, maybe I could have picked any number of equivalent theories or analogous theories. Maybe I could pick one kind of symmetry or another or another or another. Those are all kind of on equal footing, and therefore none of them are stand out as particularly beautiful. On the other hand, maybe there's a symmetry that has a special property, like supersymmetry is a great example. It is the only symmetry you can write down in a realistic theory that is both a symmetry of space-time and an internal symmetry having to do with the quantum properties of particles. That uniqueness of supersymmetry in some physicists' minds elevates it in terms of its beauty and, by association, its likelihood of being true.
So with Dan's car keys example, I can propose a theory about bees stealing them out of his bag, but I could also propose an equally valid and likely theory where a bear steals the keys, or a flock of pigeons, or a pack of zoo animals making their escape. You can make up an arbitrary number of theories like these, and none of them really stand out next to each other.
One concept that comes up when people talk about the beauty of a theory is what we call naturalness. Basically, the idea is that if there's some very contrived seeming cancellation between things or coincidences in a theory, that makes it less beautiful. So if I just took the standard model of particle physics and I wanted to explain why the Higgs boson is so light, I can arrange that by accident. I can say a whole bunch of these enormous numbers, when you add them together, the positive and negative pieces cancel, so the sum is really small for no particular reason. But that's pretty contrived, and it seems arbitrary and maybe unlikely to be true. We say that's not a beautiful facet of the standard model, and that motivates us to look for solutions to explain why the universe is the way it is.
Would you say that, in other words, it's not like the best practice to motivate changing your theory because you just want it to fit a certain expectation, or you want it to give you a certain result? And maybe the reason people say that beauty as a guiding principle leads to truth more often is that it's not contrived. It's not coming from your pre-expectations. You're kind of just following the logic, following something that comes from maybe nature or just the pure logic rather than from your own expectations or biases.
Yeah, if you're trying to explain why, something in nature is a certain way, and your theory forces you to accept that that thing in nature should be that way, in other words, it's predictive, it says it had to be that way, then that's powerful and that's beautiful, that's elegant and simple. If you get to choose when constructing your theory how that thing should be, you're not impressed that you can choose the thing that you've observed to be true. That's postdictive, not predictive.
Okay, so that makes beauty sound kind of reliable in a way.
At least it could be.
So now that we've talked about what it means for a theory of physics to be beautiful, let's get into our next big question, which is, how useful is beauty as a sort of guiding tool to physicists?
So let me take a second, Shalma, to make clear to our listeners what we are not talking about here. As far as I'm concerned, all scientists I've ever met and anyone who would consider themselves a scientist will all agree that data settles all debates. If you have a theory or multiple theories in competition, and one or more of those theories disagrees with the data, we know that theory is wrong. It doesn't matter how beautiful or elegant or simple that theory is, any theory that disagrees with the data is a wrong theory. So what we are talking about here is the question of how we should evaluate the relative likelihoods of different theories being true if they are currently untested. So we have lots of instances where we don't have the data yet. Maybe we don't have a big enough particle accelerator or a powerful enough telescope to find out if a theory is true. How do we select from among those theories the ones we think are most likely to have something to do with the actual reality of nature? So if you haven't thought about this question much before, your first thought might be that you should maybe just take a totally neutral or agnostic view among all possible untested theories. Treat them on exactly equal ground. But in practice, this isn't something you can really do. And no one does it in real life. So you start out, before you have any data, you look at the array of hypotheses you can come up with and you evaluate them. And you use certain kinds of common sense or plausibility versus contrivance to evaluate what you think are the leading possibilities. So as a scientist, I might look at a bunch of different theories I could consider, all of which are untested. And I might say, well, these sound to me like the ones that are most likely to be true. And some physicists tend to use the word beauty to describe the characteristics of those theories that they think are most likely to be true. So we can ask ourselves, related to this, is kind of a meta question. So instead of asking what theories are beautiful, we can ask, if you take the theories that scientists in the past have identified as seeming very beautiful to them, have those theories, when the data was gathered, turned out to be likely to be true? So it's not a question about what is beautiful, but does this sense of beauty as actually used in practice correlate with theories that are true?
So we are getting meta. We're testing our theory about whether
our theory about theories.
Yeah.
We're finding out if our theory about truth is true, right?
Yeah.
So you could go out and maybe collect a bunch of data. You could force a bunch of physicists to quantify which theories they think are beautiful and how beautiful, giving them numbers or something, and then wait a generation and see, if the ones that they ranked highly turned out to be true more often than ones they rank lowly. But in reality, we don't have any kind of data like this. Physicists rarely rank their theories by how beautiful they seem to be. They say some vague things about certain theories being beautiful. So we don't really have an answer to this. We do have some anecdotal evidence, I guess. I mean, you can weigh it however you want, but you can find examples like in the 1960s when Murray Gell-Mann used these principles of gauge symmetry to construct the theory of the strong force, what we call QCD, or quantum chromodynamics. And before the data came in, he said, we just knew it was so beautiful, it had to be right. I mean, that's the sort of, famous prediction that we, at least in hindsight, looks like there was something to this relationship or correlation between beauty and truth. And you can find all sorts of examples of this, especially in particle physics, where people made statements like this and then it panned out. And I would say that, like 20 years ago when I was a grad student, this way of thinking was almost unchallenged among theoretical particle physicists. We saw lots of examples in the history of physics where this just worked, where people thought a theory was beautiful and then it turned out to be true. And there were lots of theories that we all really liked, that we thought were beautiful, that hadn't been tested yet. But we were, pretty confident would mostly turn out to be true. These are ideas like supersymmetry and grand unified theories and string theory. And we kind of felt like we were kind of like Einstein in 1919, looking at these theories and saying they just seem too beautiful to be wrong. Since that time, some opinions have changed, and there have arisen a number of critics of this approach. And those critics have not only become more numerous, but more vocal. So some of the most famous ones include this mathematician, Peter Voigt at Columbia. He wrote this blog and eventually this book in 2006 called Not Even Wrong. And in that book, on his blog, he argued that string theory in particular was this dead end, and that we had applied subjective aesthetic criteria that had misled the whole scientific community and wasted a bunch of resources on a theory that probably isn't true. In the same year, this physicist named Lee Smolin at the Perimeter Institute published a different book called Trouble with Physics, which made similar arguments specifically against string theory. More recently, and probably most famously, Sabine Hossenfelder, a research fellow at the Frankfurt Institute for Advanced Studies and author of the blog Back Reaction, wrote this book called Lost in Math. And in that book, she laid out a long list of very critical arguments against beauty being used as a reliable guide for truth in physics. So I've read all these books. I've had lots of conversations with people who hold these views and people who don't. I've thought back and forth about it. I'm not an expert, but I have kind of distilled my own personal opinion, so I'll tell you what that is. First of all these authors make some good points. I'm not trying to say they're not saying anything sensible at all. And there certainly are examples in history of famous theoretical physicists making statements that like really strongly endorse a theory as almost certainly true, even though there's no evidence. And that probably isn't a reasonable thing to do. There are lots of theories that seem beautiful at the time and turned out to be false. But on the other hand, I think for the most part, these books are really just building up a straw man to argue against. And that straw man doesn't really reflect what many real theoretical physicists think about this correlation between what we call beauty and truth among physical theories. Like, as I've said before, every scientist I've ever met agrees that the data is the arbiter of truth. We don't care if a theory is beautiful, if it's also empirically wrong. The debate is just about what we do with all the theories that we haven't been able to test yet. And like, there's good reason to think that theories that are elegant and simple and non-contrived and whatever are more likely to be true than the others. And if you want to take a neutral view, that just doesn't work. We have to decide what problems to work on and where to put our resources. We need to decide how to, give out grant money. Which theories are we going to pay to have researched? And most importantly, which experiments are we going to run to test which theories? We don't have enough money to test every theory. So we have to make some sort of subjective guess or judgment about which theories are most important to spend that money and hours of professional, study to investigate. So this means we need a criteria. And if there's a better criteria than the one we're talking about here, I'm yet to hear it.
Yeah, I mean, I think I have no problem with the idea of beauty in physics. I think that's fine. I mean, we're all human, and if certain ideas are exciting or make us feel good or something, I think we should welcome that, and that should be like a welcome part of the process. I guess, maybe I hope that people just take this to realize maybe, like, I think there's a lot of mythology around like physics and science being this like completely objective process. And I mean, like, our results are objective. Like, I mean, and as long as you're honest about your assumptions and like your methods, then like, yeah, the data doesn't lie. But like the process of doing it and the process of, choosing which things to work on and the process of awarding grants and funding and things like that, that's incredibly subjective and just a function of society and the people who are doing the physics. So I have no problem personally with beauty being a guiding force as of my knowledge right now, as long as people don't go too far and think that their sense of beauty is objective or, is like more universal than just their own experience.
You mentioned the mythology behind the idea that scientists are all like purely cold and rational or something.
Yeah.
But there's another kind of mythology that gets told a lot, which is that it's almost mystical. And like, this inspiration comes to them and something that could never be reasoned out came into somebody's mind and it just all played out. And like, well, that's not really true either. Both of those kind of mythologies are exaggerated. The fact is, we're human beings. We're working with our human brains. And we try to apply reason and rational thinking when we can. And the rest of the time, we kind of use our intuition and guesswork and, our best hunches to, random walk towards the truth.
Right. It is a random walk towards the truth, I guess.
All right, so let me close with my favorite example of beauty being misleading to somebody trying to do physics. So this is a story of Johannes Kepler. He's one of the most important astronomers of all time, so he's working at the same time as Galileo and other people like that. And, he's famous for his 3 laws of planetary motion that say things like planets move along ellipses and not circles. And they tell you how fast planets will move at different points along their orbits and things like this. Really important work. But Kepler died thinking that his greatest contribution to science wasn't these 3 laws of planetary motion, but this other theory he had published describing the solar system based on these mathematical objects known as the Platonic Solids. So the Platonic Solids are these 3-dimensional shapes. They have identical flat sides with identical edges. And it turns out there are exactly 5 kinds of these. Like mathematically, there are exactly 5. There's not a 6th one. So there's like a 4-sided pyramid, the tetrahedron. There's a 6-sided cube. There's an 8-sided octahedron, and there's a 12-sided dodecahedron and a 20-sided isohedron. For anybody like myself who's spent a lot of their life playing Dungeons and Dragons, this is the standard D&D set of dice. So you might find that familiar. But it turns out, Kepler figured out that if you took a sphere, encased it with one of these Platonic solids, put another sphere, then another Platonic solid all the way out. So you have 6 spheres with 5 Platonic solids between each of the 6 spheres. And you put them in the right order. You have to pick the right order. Then the spheres have a ratio of radii, which is really similar to the ratio of the radii of the orbits of the 5 planets or 6 planets that were known at the time. So Kepler thought from purely geometrical principles, like things you could write down on paper and you didn't have to measure anything, you could deduce the whole structure of the solar system. Of course, it's all nonsense. None of this is true. It was just a coincidence that these, 6 orbits or 5 ratios of different orbits were like qualitatively similar to this Platonic solid exercise. And as the data came in, it turned out to be more and more clear. It just wasn't true. But to Kepler, it just was this gorgeous, elegant, simple, beautiful explanation for why the solar system was the way it was. So beauty, even when it seems really strong, can have nothing to do with reality in certain historical examples.
Right. I feel like this is almost a common movie plot. I don't want to spoil any movies, but mathematical genius who goes a little crazy and starts seeing patterns that aren't there kind of trope.
Yeah, there are a lot of them.
Yeah.
One of my favorite movies of all time is Darren Aronofsky's Pi.
Oh, I also really loved that movie in high school. That was my favorite movie for a while.
I think if you took all the people who said that was their favorite movie, there's a large fraction of them are physicists or mathematicians.
Mm-hmm. So what do you think? Should beauty be a guiding principle for physicists? We'd love to hear your thoughts on Twitter or on our Patreon. And until next time, thanks for listening to Why This Universe. Our show is produced and edited by me, Shalma Wegsman, co-hosted by Professor Dan Hooper of the University of Chicago and Fermilab, and all music is produced by Jake Kleinbaum. Why This Universe is brought to you by the University of Chicago Podcast Network.